Then there's the last thing that we have to calculate. How can you calculate the thermal efficiency? So can you calculate the thermal efficiency from all values that we have calculated so far? What do you think? Let me delete all this one again. So please think about how to calculate the thermal efficiency. Have you thought about it? Now, your thermal efficiency, okay, in general, for heat engine, can be calculated by having a desired output, in the case the net work, compared to the required input, in the case Q in. So let me write it down again. So the thermal efficiency can be calculated by dividing the net work with heat input. And we already know the W net, and we are given this heat input. Okay? So easy. By applying those numbers that we already know, that gives us 51.8%. Okay, so now I'm done in calculating the example problem that is given. And I hope that now you understand how to do that thermodynamic analysis for the ideal Otto cycle. Okay, so remember that the whole objectives or goals of doing this type of analysis is to, first to get the power output calculation done. Okay, so you always want to calculate how much net work can be produced by that cycle. And second thing that you have to do always is to calculate the thermal efficiency, how efficient your cycle is. Okay, so that is what you have done. So in order to calculate the work and efficiency, we actually have to calculate we have to know the pressure and temperature and even specific volumes of each state. That is the whole first part that we have done. Then let's discuss a little more about the thermal efficiency. Now I'm sitting, chair, and then I just want to use that slide to discuss more about thermal efficiency. Okay. So again, we calculated thermal efficiency after calculating the net work and heat input. Okay. Now we actually can do the exactly same thing, but by using the ideal gas assumption and constant specific heats. Okay. And if you do it carefully to calculate the thermal efficiency in terms of symbols, then you have this equation, okay, for the ideal Otto cycle. You must remember, however, that this equation is only valid for the ideal gas with constant specific heat. Yes, we use this assumption. So if we use this equation, okay, then you can get the exactly same value for the thermal efficiency as the value we calculated by using the net amount of work and heat input. But if your working fluid cannot be assumed to be constant specific heat anymore, or in other words, if you use the fact that your specific heat actually should vary, and yes, it varies, then you cannot use this equation. Okay? So I really want you to remember the limitations of this equation. But there is a strong benefit of using this equation. By the way, I'm not going to do any derivation of this equation, but that will be your homework. All right. So, and also, in fact, one big hint is that derivation of this equation is already given in your textbook. So please make that chance this time as a chance to read your textbook to find out the derivation, and that should be your homework. All right. Now, the benefit of this equation helps us, understand better about how we have to design the spark ignition engine. Okay. Obviously, by looking at this equation, then we can instantaneously realize that this efficiency of your engine is solely dependent upon your compression ratio. Okay? Let's not worry about this K at this moment. So we can draw the plot as you see in the left bottom side. So your thermal efficiency of the ideal Otto cycle is sole function of compression ratio. So that's why I said before that the compression ratio is the key designing parameters of your spark ignition engine, because it does tell us how efficiency can change for your compression ratio decision. And it increases as the compression ratio increases. So what does it mean? So in order to have the better efficient, the more efficient spark ignition engine, you basically have to increase the compression ratio. Okay. Now I'm gonna come back to this plot, but at this moment I'm gonna just talk about the effect of K value. So also we can change K. Okay. Then if you increase K value from 1.3 to 1.667, then you can increase the efficiency even at the same compression ratio. Okay. So what it means is, oops. Okay, let me just use the annotation. I'm not sure if that's kind of my first time I use this annotation, but all right, here we go. So now we want to increase the K value. In other words, we want to increase the specific ratio, because that gives us higher efficiency for the Otto cycle, the engine, even we have the same compression ratio. Then how can you make it happen this way? How can we increase K value? Okay. So the K value can increase if you really think about what we have to really deal with is the fuel and air mixture. And depending on this ratio of fuel and air mixture, we can change the K value of your effective, the working fluid. Okay? And as we increase more the amount of air, we can increase the K value. So what it means is that this direction is more going toward lean burn condition. Okay. So I'm not sure if you remember, basically that's kind of old story. But when I was, high school student, there was a big key. I mean, some car companies actually tried to sell lean burn engine. Okay, and this lean burn engine actually follows this design concept. Okay, they wanna burn less fuel to make the efficiency of that car engine much higher. And then, can you guess? Guess what? Guess what happened to the car? What do you think? Was it a big success or a big failure? Now you can clearly answer the question, because now you don't see that lean burn engine anymore these days. Yes, that was a big failure. Why? Because now, yes, you can make your engine very efficient by burning less fuel. That's cool, but at the same time, because you burn less fuel, your power, decreases drastically. So that engine, even though that has really, really nice efficiency, but at the same time, this engine power is so low, so it's not fun to drive. And yes, we sometimes drive a car for fun. We want to have really fast and furious car driving experiences, but that lean burn engine does not satisfy your expectations. So that's why, even though with a very high efficiency, that lean burn engine, it was kicked out of the market. Okay, it's funny, right? So now let's go back to that. So now here we go. So again, we want to increase compression ratio more and more and more, okay? Because apparently it tells us that the more compression ratio we design the engine, then the high efficiency we expect. And that is, yes, that's true. That's kind of from the physics. But the problem here is that the gasoline engine is limited in terms of the compression ratio. And as I said kind of in the previous lecture, the compression ratio of spark ignition engine is limited from around 8 to 11. So 11 is around the kind of maximum, the value of compression ratio we can design for the gasoline engine. The question is, why? Why is that compression ratio for spark ignition engine is limited up to around 11? Okay. Then we can find the reason in the next slide.